Well, good day, everyone. So thank you for joining us and welcome to Cozy Lab's roundtable discussion on the importance of software in particle therapy and why is it even considered to be the hard part of particle therapy. My name is Gregor Humar and I serve as the Vice President of Medical Division at Cozy Lab, and I will be your host today. So for those of you who don't know Cozy Lab, we are a group of over 250 experts specializing mostly on developing full stack radiotherapy software solutions. Our product suite, called Oncology One, covers all the needs of a PT system, from low-level control, like control of an accelerator, for example, through safety system and real-time control, like pencil beam scanning, to clinical systems, like patient position verification system, R&V, or some people call it treatment control system, and oncology information system. I'm very honored to welcome our guests today, Dr. Jay Flans, Dr. Zhu-Feng Li, and Dr. Thomas Rock-Mackey as the panelists of this roundtable. Each of them is a very prominent name in particle therapy, and let me give each a brief introduction. Dr. Jay Flans served as associate professor at the Harvard Medical School and technical director at the Francis H. Burr PT Center at the Massachusetts General Hospital before retiring in 2020. He is the president of the PT Cock International Organization. Dr. Zhu-Feng Li is the chief physicist of the Maizong Jiahe Medical Group and the Guangzhou Concord Cancer Center. He is also a fellow of the American Association of Physicists in Medicine and was a member of the PT Cock Steering Committee. Dr. Thomas Rockwell-Mackey, known as Rock, is an emeritus professor in medical physics, human oncology, and engineering physics at the University of Wisconsin-Madison and the Director of Medical Devices at the Morgridge Institute for Research. From Cozy Lab, we have Dr. Uroš Mitrovic, who is the Medical Product Portfolio Manager of Oncology One product suite. And Uroš has a PhD in medical image processing and is the author or co-author of several papers in prestigious journals, conference proceedings, and US patents. So welcome again to all the panelists and also to the audience. And let's start the discussion. Well, we all know that particle therapy machines are highly complex devices. And our experience is that integration of various subsystems into a complete system is very often heavily underestimated. Maybe a good example is the complexity of an accelerator, beamline, and dose delivery system. Jay, what do you think is the impact of integration of all these systems on the performance of the overall system?
Thanks for that question. I think that's a very important question, and because I think there's a lot of misunderstanding surrounding that. So maybe it's not a big surprise that I have a slightly different take on this. Of course, there are many subsystems and they have to be coordinated in a way to do a treatment successfully, but not all of them. And I guess my experience would be that some systems are actually too tightly and sometimes badly integrated, and not because it's hard to do it right. The worst part is that some of the behaviors of subsystems have been made to depend upon signals from other subsystems or other parts, and they're done inappropriately. This type of integration makes it all but impossible to debug an unwanted event. I'm not saying it's necessarily a safety issue. Safety, for the most part, is a separate story, and we'll talk about that. But there's an important part that's left, and that's the operability and reliability of systems and annoying repetitive events that can cause real problems in performance. And these are sometimes hard to find and fix if the controls, hardware and software, are not properly architected. I have a general rule in control systems. If more than 5 people are working on it, then it's destined to have problems. What if the integration is too tight and the system hasn't been architected properly and modularly? Then software of one of the 100 people working on it has a behavior that one of the other 100 people didn't expect. And either because they didn't interpret the specifications correctly or didn't read them or they didn't exist. One example we had at MGH was that there was a specification that said that the gantry should not start moving unless the aperture door was closed. And that was interpreted quite literally So very quickly, the therapists found that all they had to do was shut the aperture door to start the gantry moving, and then they could open it up again and do whatever they wanted to. That was not a good situation, but it was an inappropriate specification of the controls. So I may not be representative of others here, but in a previous life, once upon a time, I was an accelerator physicist. And I don't think that accelerators are complicated to operate to get beam. But I do think there's some amount of secret sauce in some systems, and it's the lack of clarifying those secrets that makes the controls harder to be simplified. What's complex are the things that most accelerator designers don't know about, like controls related race conditions and indeterminate state machines. For years, I was advocating automated operatorless operation of our cyclotron, and I kept being told, oh no, it's complicated, it's complex. So I took it on myself and delegated one young engineer who knew Python, and in 3 months, we had a fully automated system. Scanning is another example. I once wrote a beige paper and to help with specifying the generic process of scanning, hoping it could be used by industry to better architect their systems and produce more flexible features and better integrate with OIS systems. Unfortunately, this was kind of ignored. And when we were told that a full system reworking was needed to upgrade to scanning, even though we had uniform scanning operational, I had to take that in my own hands. And with some talented help, in 1 year we had scanning and another 6 months FDA approval. So who says it's complicated? Not everyone may have the same take on that. And part of the reason this is the case is that current systems are, for the most part, developed as though they were in high energy physics laboratory machines, with the emphasis on the components of these machines. In a radiotherapy system, it's more important to concentrate on the flow of data and understand what information is needed, how best to use it, who needs it, and display it, and identify its role in safety. Much of our earlier issues before we began patient treatment was blamed on software. That was wrong. The complexity that is believed to be existing is, in my opinion, a lack of full understanding of what's needed. Integration is important, but only the appropriate integration in between and amongst all the correct components. With each new generation of software engineers, the same mistakes are made. Only with a group that's experienced and knowledgeable and will listen to the right experts with an open mind can the situation improve, in my opinion.
Thank you, Jay. And we'll be talking about some of the areas specifically in the further discussion. How about you, Urosh? Do you have anything to add here? I mean, since you have been involved in many integration projects COSALab has done throughout the years for various PT machines manufacturers.
I must say that Jay covered the topic very well. What I can say from my experience by talking with our different customers is one of the pitfalls is that when they're planning to build a PT system, they're thinking, I will buy commercial off the shelves, put them together, and then having a working system. And this is, it cannot work in this way. And only then they realize that this integration is quite important. And what is here really a technical problem is that all these independent devices, they have their own communication protocols, they have their own behavior, yeah, they have their own internal states, workflows, limitations. So basically, when you're building a PT system, you're for the first time putting all these different devices to form the whole system. And this is something what we are doing at COSALab for the last 20 years. This, I can say it's like an art to make all these different components in a meaningful and efficient clinical workflows.
Yeah, thank you, Urosh. I mean, since we're talking about workflows, let's take a bit closer look at the role that performance software plays in efficient clinical and QA workflows. Zulfeng, what is your take on this, given your abundant experience with various workflows?
I think that was exactly what I was thinking about. I think Jay and you both mentioned it very well, described very well on the underlying concerns, the issues of the communications between the components of the independent systems. As a clinical medical physicist, I am, I think what I see, how I operate, can be the kind of the final door in evaluating a piece of software, the usability, how it fits a clinical flow, and when it's not fitting, how easily can it be modified, or can the, we are kind of creatures of habit. We in radiation oncology, we have therapists, we have physicians, we have physicists. We all work together. We each will trend in a certain way, and we have this particular flow of things or use scenarios that we expect. The issue is that when we introduce something that is totally against the intuitions of the users, I think that can be risky. There is a safety concern. There was actually a recent publication on the on the arrangements of the computer screens in a radiotherapy treatment room, and how that affects either safety or working efficiency. I think that's to me is one of the major, in terms of user interface, how to interact with individual pieces that are integrated together. What are the sequences? How do I get a job done with a minimal number of mouse movements and minimal number of keystrokes with no failure? I think that is something I would expect that, I mean, it's tough. The issue clearly is that in different countries, for example, we do not always have the same workflow. So that in itself is a major challenge in designing the good piece of software. And we all know about the incident of the Serotron incident that back in the 1970s had a safety issue that when they tried to switch from a electron mode to a photon mode, they didn't. They moved the key too fast, and the computer did not catch up with the command, so that the target wasn't put in, and the patient was treated with a electron beam that's 1,000 times higher in influence than would have been in the photon world. And that's kind of the issues I think we need to keep in mind. We always need to look into all the details of integration and try to prevent user errors. And one of the best ways to prevent user errors is to try to stick to something they are familiar with that comes natural to them.
Thank you. Let's still stay on workflows for a bit. Rock, looking from a workflow perspective, PT and conventional radiotherapy are pretty similar. However, when you enter treatment, the treatment control rooms are quite different. So why do you think this difference exists? And what can we learn as developers of PT systems from conventional RT?
I mean, the fundamental problem is that what you're doing is adding control system onto control system onto control system. And fundamentally, a human has to interact with those control systems. And typically you're looking at multiple monitors, and a person can only look at one monitor at a time. And so good, well-integrated radiotherapy systems have no more than two monitors, one for interacting with the control aspects, patient selection, what you're going to be doing, and then image display. In fact, the image display should also include just a conventional camera display of the patient as well. Again, you can only look at one thing at once. And it's often good. I mean, some folks say, well, we have lots of therapists around, each one can be looking at a different thing. But really, you really want everyone to be engaged in looking nearly at the same thing that's relevant at that instant in time. And an automobile is a good example of a good workflow. You're essentially, you're looking to see what traffic is coming. Occasionally, you'll look at a different part of the view. You'll look in the rear view mirror and the side mirrors. But you know what? Your attention is on one thing at one time. And if we could only design systems that really inherently dealt with the therapist as a individual that can only think about one thing at once. And then the other fundamental problem, I think, with protons, in fact, even goes back into treatment planning. We fundamentally treat protons as if it was a fundamentally different radiation therapy modality. And the reason for that is that the Bragg peaks are where the very high dose part occurs, and the slightly higher LET part. So we're so terrified of putting a Bragg peak in normal tissue that this very high resolution part of the beam we almost never use. And the fundamental problem there is we don't know where the Bragg peak is to an accuracy that allows us to do more conventional based treatment planning. And so, for example, I know that Cozy Lab is working with Proton VDA on proton radiography, and the folks who have worked with them at the Chicago Northwest Proton Center have showed that you can control the Bragg peak to within a millimeter based on proton radiography for brain, head, neck, and the thorax. So what we really need to do is we need to think of a holistic picture and say, fundamentally, we have this great high resolution structure called the Bragg peak. How do we use it effectively? And so, it comes really, even some of the problems in proton radiation therapy come around to the very fact that we're afraid of what we brag about so much, the Bragg peak. So I think there's ways to improve it. Fundamentally, you have to start with full integration and not have disparate control systems. As Jay says, trying to communicate with each other and coordinate each other. It takes very good architecture to simultaneously have good unit-based software control and fully integrated software control. So it's a little bit of art, a little bit of science, and the architecture is so important.
Thank you so much, Rock. Now I'd like to put some focus on the most safety critical systems in a PT machine that were mentioned already before. And those are the safety systems. So meaning both patient and personnel safety system. Jay, in your opinion, how important is the role of software here?
So you're right. Safety is certainly the most important aspect. I certainly agree with that. How critical is the role of software? And that has been an evolving theme in my life over the last few decades. I remember, first of all, that a non-working machine is not safe, right? So since the patient is not getting treatment. And in the beginning, I believed that the software role in safety was actually a tertiary or a higher redundancy. Wires and AND gates were more reliable and the logic was more tractable. And so it was never acceptable to use software as a mitigation for a highly severe hazard or a fault that was highly probable. But why is that? I mean, software runs as it is written. And that must mean that either it wasn't written well or that there are variables in how it runs which aren't explicitly embedded in how it's written. So I think some confusion and lack of understanding of that has turned software into something which was not fully used for safety in that way. I still do believe that it runs as it is written, including all of the implied timing issues and integration issues that might be built into it. But again, that's a function of how good the software architects are and how well they've incorporated what's important in the design of that system. And so it doesn't mean that a person who is at a accelerator control system knows how to do that. They know how to set magnets and turn on beam, but they don't necessarily know how to understand all the embedded implications of a software system. And then software became an even more important part, in my mind at least, of the safety when scanning came about, because one needed to do an analysis to enable the handling of statistics, noise, glitches, without unsafely stopping the equipment. You couldn't just do a binary stop or not stop because you would just never finish the treatment. It could be part of a 2 out of 3 logic, or it could have been used to decide that something is safe, even if you think it really isn't safe, or vice versa. So the whole subject of error handling is a much ignored topic, and it's never really been done well, to my knowledge. And it has never been done well by the people who are building PT control systems with the rest of that system. I mean, it needs to be done by people who understand it and know it. However, I actually came more recently to the conclusion that software can be even more effective if it's used as a skeleton iron dome, right? Thinking more like the Star Wars program. If you have a skeleton on the outside that's watching what's going on, there's a lot of possibility if it gets put in the hands of the right people.
Thank you, Jay. Uroš, you've been involved also in the development of many different safety critical software projects for PT systems. So what are the lessons you have learned along the way?
Here, I will agree with Jay that actually software plays more and more the more important role also in the safety. So going from traditional that you have a harder risk control measures, more and more risk control measures are also implemented in the software. For instance, with a recent introduction, let's say, of AI stuff for contouring or for the image registration for the IGRT, you have here the pure software risk control measures. And to rely on software, you need to, as Jay said, you need to have a reliable, well-written software. And to do this, basically, you have a lot of medical standards which you need to follow. So software development for particle therapy system is very complex. Because to write the software for particle therapy itself, it's very complex. You need to understand the domain and all these relations between different devices. And B, all these processes are very strict, and risk management plays the central role. So basically, at the end, your software needs to be really thoroughly and well tested. From the unit level to the system level, you have a unit test, code reviews, static analysis, integration tests, system integration tests, workflow testing, end-to-end testing, a lot of testing. At the end, of course, you have a BMV, and all of this that at the end you can say and prove that your software is safe and efficient to be used for the patient and personnel.
So I'd like to move the discussion also on PT system upgrades and the role of software within the upgrades. And since the introduction of particle therapy, PT systems have gone through a number of changes from one generation to the other. Typically, existing, that means a running PT machine, rarely goes through an upgrade stage, especially due to the high cost of downtime, right? What role does the software play in a PT system upgrade, and how does it impact an optimal design for upgrades? Jay, what do you say about this? As a technical director, you have been involved practically in the whole life cycle of the machine in the birth center, right?
Yeah, and we don't have enough hours to really discuss that topic. That's like half of my life devoted to that topic. On the other hand, now, you think about it, we now have about 110 particle therapy facilities in the world. And most of the world has sort of evolved into the scanning modality. So unless things like flash and microbeams become even hotter, a lot of the change that we've experienced might be slowing down. I'm not so sure, but it might be. We've certainly evolved beyond the infancy stage in terms of system capabilities. And although there's always a reason to replace a LINAC every 10 years, I'm not so sure that's the same with a particle therapy system. But there will be more improvements, like better real-time imaging, particle-based imaging, for example, and adaptive therapy. So let me come back to that in a second. These things should happen on the base of what exists. And some people might say intrinsically that's not possible. I say it should have been possible. And that's the rub. Because of the integration issues that we've already discussed, because of the way the systems have been architected and specified, we're not there yet. If that beige paper that I wrote had been treated more seriously, I think things would have been different now. Take a patient positioner as an example. It has 6 numbers that are needed to be exchanged. And except for collision issues, that is all. And I just have to repeat it. That is all. Yet in some systems, it's an act of heaven to enable a replacement of that kind of a system with downtime and all that. You should be able to pull it out in the weekend, put in the new one, hook up those 6 wires, and that's it. But the systems are not built to do that, even though it's possible to do that. Or a process, for example, like scattering, is so tightly woven into the software that making it necessary to completely replace entire subsystems to upgrade to scanning. I developed this concept called treatment point concept, making the concepts of the room, modality, delivery, all generic, so that it was just a question of upgrading the hardware and not so much the software. But it wasn't really accepted. But I guess change is a question of vision. It's only considered change if it wasn't originally envisioned. So in fact, in all these upgrades, software has always been blamed for the most difficult part to upgrade. And how much of this was due to the fact that software engineers never stay in the same place too long, and therefore the system knowledge is lacking by the people when it's time to do the upgrade, or that's something else. That's why it's a much longer conversation. But with a properly architected system, a properly modular system, and a properly thought through system, it wouldn't be such an issue to upgrade. And maybe that's discussion happening later, but that's when outsourcing might become important.
Thank you, Jay. Zhongfeng, do you have an opinion on this from a clinical user perspective?
Yeah, that was a very interesting question. That's something that, frankly, I do wish that the vendors would have done better. As Jay mentioned, the system software, many of them were designed from the beginning not with future upgrade in mind. Therefore, the system were not really modularized enough. I mean, that's impact particle therapy even more, because I have several treatment rooms. And if I'm just upgrading one room at a time, I cannot do that, because the entire system need to be done. It needs to be done to be put into a testing mode to allow you to upgrade to something that does impact the entire system, but the rooms were not separated enough to allow me to treat patients in other rooms while the upgrade is going on in one room. I mean, that part that can never be done separately anyway, right? I mean, if you cannot upgrade a cyclotron without impacting all the rooms together. I mean, I accept that. But I just wish that we have all spent more time, the vendor side, especially software designer side, to modularize the things, to kind of put them into their own little cubby holes, so that you can plug, maybe not plug and play, but at least have a little bit less damage on the entire operation. I mean, there are vendors that would refuse to provide any upgrade support. You basically cannot upgrade anything at all, just because the software design, I think it's more software, because some of the upgrades were just totally localized to one room, just like Jay mentioned, upgrading the patient position in one room, or install CBCT in one room. You cannot do it. I mean, I can't believe it. It just hurts there will be future upgrades coming in, and there's no question in my mind that we will see future upgrades for any particle system. I mean, it's a system with 25 or 30 years of life expectancy. There's no way you can get away from that. By 30 years from now, maybe Microsoft wouldn't exist anymore. What do you do then? Or Linux, maybe bought over by some company, you cannot use it anymore. Who knows? I think everybody wants you to keep that in mind. And the first consideration, of course, remains safety. But I would like to have the clinical impact of a non-operating system for an extended length of time. I mean, we look at the upgrade. If our entire system was down for 3 months, effectively will be down for 1 year, because it takes time to ramp down the patient and takes time to get the patient back. And by that time, the center is closed already. I mean, you're bankrupt. I think it's significantly important. There's no question about it, and everyone really need to be have some good thought about it.
Thank you, Zhongfeng. Rock, from the manufacturer's point of view, what are the factors which impact the PT system upgrades, in your opinion?
Well, I mean, I'll talk about radiotherapy systems in general again here, and fundamentally, you should not upgrade everything at once. I'm a firm believer in having good divisions between systems. So, for example, in the case of proton radiation therapy, the beam delivery, the beam steering, everything that gets the beam out of the nozzle is separable from everything that positions the patient, from verifies where the patient is. And so those two systems should be fundamentally separable And of course, you need a model of one, but you could replace the patient with an orange crate and a phantom, and the beam should still be delivering in exactly the same way as if there was a patient there. And then the patient should be moved around and imaged independently of whether it's a proton beam or a radiotherapy beam. So there's a nice separability possible there. So splitting it into functional things like that. So of course, the verification of where the patient is also used to verify where the beam is. So those two systems should probably be upgraded in two times, because the older system can help verify the newer system. For example, in tomotherapy, we introduced a beam checking system. We had a detector that was used for megavoltage CT, but it intercepted the megavoltage beam, and that was extremely useful for verifying where the beam was. So we took to not upgrading the control system of the accelerator and the verification system of the accelerator at the same time. Because in one case, you want the verification system to be in the state where it can detect any small changes in the beam that you've just implemented, and vice versa. You want any upgrade of a checking system to give you the same results if the beam is unchanged. So just clever ways of upgrading a system. I also believe you shouldn't upgrade a treatment planning system and a radiotherapy system at the same time. They're separable, and one helps the other verify the other. So simple things like that. It's good obviously to have very close coordination between software suppliers, or ideally have the same software supplier that understands the whole system. So having one partner, Leo Cancer Care, which I founded a couple of years ago, is partnering with Cozy Lab because of its broad knowledge of proton radiation therapy and the entire proton radiation therapy treatment workflow, from treatment planning through to accelerator control, on to record and verify, and so on.
So thank you for the insightful debate. We'll take the questions later via chat. Thanks again to the audience, and please don't hesitate to contact us for any follow-up questions. So thank you and take care.